So what we're going to do today is we're going to look at the unit circle, and we're going to look at putting a whole bunch of information on our unit circle. In particular, there's certain angles that you can do sine and cosine and tangent of without your calculator. And that's what we're going to try and develop today. So a little bit of review about the unit circle. This is your unit circle. Its center is right at 0, 0. It's called the unit circle because its radius is 1. And on this piece of paper, we've separated a bunch of different angles according to certain families or groupings. And the first family we're going to look at is the axes family. So the axes family is concerned about the points on the unit circle that intersect with the axes. So there's 4 points on the unit circle that intersect with the axes. And if we start with the easiest thing, which is probably degrees, and we think about angles in standard position starting from the positive x-axis, and we just go once around, does it make sense that this would be 0 degrees, your positive x-axis? Your y-axis would be 90 degrees, 180 degrees, 270 degrees, and if we went all the way around, 0 degrees would be coterminal with 360 degrees. We could keep on going, but we'll just go once around the circle. So I made my legend. I said I was going to make my degrees in blue, so I labeled them in blue. I'm not going to draw the little arrows to the angles because it's going to get really full. Because we're going to put degrees on here. Next, we're going to put radians. So again, starting with 0 radians here, what's 90 degrees in radians? Pi over 2. 180 degrees, that's pi. 270 degrees, that's 3 pi over 2. And of course, going all the way around, 360 degrees is also 2 pi. So thinking about the unit circle and thinking about the center being at 0, 0 and the radius being 1, what are the coordinates of that point? 1, 0. And up here, 0, 1. Moving 1 to the left, the coordinates of that point would be negative 1, 0. And finally, 0, negative 1 here at the bottom. And this is where one of the big ideas that we had from earlier comes into play. You know that the coordinates on your unit circle are cos, sine. So just by labeling these coordinates and labeling our degrees and radians on our axes, we can now do a bunch of mental math without our calculator. I can ask you, what's cos of 90 degrees? And you look on here, and where's 90 degrees? Well, that's right here. What point is on the unit circle at 90 degrees? 0, 1. And if I want to find cos of 90 degrees, should I look at the x-coordinate or the y-coordinate? It'll be the x-coordinate. And so cos of 90 degrees is 0. If we wanted to find cos of pi, find out where pi is, we look at the coordinate. Cos is the x-coordinate. Cos of pi will be negative 1. Sine of 270 degrees, negative 1. Because sine will be the y-coordinate. And so now we can do all of that mental math just by looking at the coordinates. And we don't need our calculator whatsoever for any of the axes families. In addition, we had the big idea that tangent was sine over cos. So if I go to 0 here, and when I write tangent on all of these, I'll write it the angle in radians. So tan of 0 is, well, if tan is sine over cos, and sine is the y-coordinate, and cos is the x-coordinate, we can say tan is going to equal 0 divided by 1, and 0 divided by 1 is 0. And sure enough, if you checked on your calculator, tan of 0 is 0. If we go up to pi over 2, or 90 degrees, and again think that tan is sine over cos, which is the y-coordinate divided by the x-coordinate, we're going to get 1 divided by 0. What's that equal to? That's undefined. It's not possible. So we'll just write undefined here because you're not allowed to divide by 0. But when you get back to pi, tan of pi, 0 divided by -1, that'll be 0. And tan of 3 pi over 2, it'll be -1 divided by 0. That doesn't work again. So we'll get undefined again. This is our axes family. So now we can do sine, cos, and tan of any of those angles, radians or degrees, without our calculator. Because we just have to think of those points on the unit circle. And those points were easy to label because we knew our radius was 1, and it started at the center of that circle is at 0, 0. Our next family is the 45-degree family. So with the 45-degree family, all of these points on our unit circle are all points where the reference angle is 45 degrees. I wanted red to make those points because the coordinates are red. What I would like you to do is you have some space somewhere on this page, either up here or down here. What we're going to do for a 45 degrees in order to figure out what sine, cos, and tan are is we're going to look at a special triangle for 45 degrees or pi over 4. If we want to find sine, cos, and tan, we know sine is opposite over hypotenuse, cos is adjacent over hypotenuse. That happens with a right angle triangle. So if I create a right angle triangle and make one of the angles 45 degrees, what's the other angle going to be? 45. Besides being a right triangle, why is this triangle special? What's it called? Isosceles. An isosceles triangle has what? Two angles of the same and two sides that are the same. So if these two angles are the same, that makes these two sides the same. Now the beauty of trigonometry is it doesn't matter how big or how small a triangle is. If you have a certain angle, like 45 degrees, sine of 45 degrees, the opposite over the hypotenuse, is always the same ratio, no matter how big or how small that triangle is. So what that allows us to do is it allows us to pick any number we want for one of these sides. Now there's going to be, as far as doing the math, there's easier numbers to work with and harder numbers to work with, but whatever number you choose will work. I'm going to show you what the easiest number is to work with. We're probably going to use 1 here and 1 there. And then if you have both of those sides, a squared plus b squared equals c squared, you're going to get the square root of 2 for your hypotenuse. Now that we've labeled those sides, you can say we've just figured out sine of 45 degrees without our calculator. In fact, you could say we're smarter than our calculator because if you go from your triangle, sine of 45 degrees is opposite over hypotenuse. For this one, when we write things, we are going to rationalize the denominator, so multiply the top and bottom by root 2. So we can write it as root 2 over 2. We'll write it like that often. If you wrote 1 over root 2, it's not wrong. You don't need to have it rationalized. But for our purposes, we'll write it as root 2 over 2. Same thing, we can figure out cos of 45 degrees is also going to be 1 over root 2 or root 2 over 2. And tan of 45 degrees is 1 over 1, which is just 1. So we did that all without our calculator, using that special triangle with 45 degrees and knowing something about isosceles triangle. And where I said you are now smarter than your calculator is that if you type in, if your calculator's in degrees, and you type in sine of 45 and push enter, it will give you a decimal. I think it's decimal 707 or something like that. That's rounding. Your calculator always rounds. It has lots of decimal places and it's accurate, and it even stores more decimal places than you can see on your screen, but it is rounding it. And what we have here is an exact value. That square root of 2 over 2 is called an exact value because you didn't need to round. You could just leave it like that with the square root. So now if we go back to our circle with the 45 degrees, and we start with blue, which was our degrees, because that's the easiest thing. This first angle is going to be 45 degrees. What is this second angle going to be if it also has a reference angle of 45 degrees? 135. How did you figure that out?
180 minus 35.
So you could go 180 minus the 45, and you get 135.
Plus 90. 45 plus 90.
Well, remember that a reference angle only is to the nearest. It happens by coincidence to work with the 90, but you always use the nearest x-axis. So for this one in quadrant 3, you would go 180 plus another 45. That would be 225 degrees. And here, 360 minus your 45, 315 degrees. Now, hopefully, you're pretty good with degrees because you've used them for most of your life. With radians, this is going to be a little bit tougher because you're just not used to them yet. So 45 degrees is pi over 4. What is the angle here in quadrant 2? 3 pi over 4. And you did that the same way. You said to yourself, well, all the way here, normally I did in degrees, I did 180 minus 45. So in radians, I'm going to do pi minus my reference angle of pi over 4. But if I'm going to subtract those two things, how do you subtract fractions? You need a common denominator. So I'm going to have to change the pi to 4 pi over 4. And then 4 pi over 4 minus 1 pi over 4, that will give me 3 pi over 4. What do you have to do in quadrant 3? You'd have to go 180 plus your reference angle. So we have to do pi plus our reference angle. Again, get a common denominator. 4 pi over 4 plus pi over 4, 5 pi over 4. And in quadrant 4, well, in quadrant 4, normally you did 360 minus your reference angle. So now you're going to do 2 pi minus your reference angle. But again, you need to have a common denominator to subtract fractions. So 8 pi over 4 minus pi over 4. That angle will be 7 pi over 4. Now that we've got both our angles on there, we can write our coordinates. And our coordinates, again, from our big idea, our x-coordinate is always cos of theta. Our y-coordinate is always sine of theta. So if you look at your special triangle, what's cos of 45 degrees? Root 2 over 2. And sine of 45 degrees also is root 2 over 2. That's because, and you don't have to draw this in, but if you draw back to your nearest x-axis, you make your special triangle. And in quadrant 2, if you draw back to your nearest x-axis, you make the exact same triangle. So in quadrant 2, cos and sine are going to be the same. But now, what happens to an x-coordinate in quadrant 2? It's going to be negative. And your y-coordinate stays positive, which fits with your cast rule. In quadrant 2, cos is negative and sine is positive. In quadrant 3, same triangle, but both your x-coordinate and your y-coordinate would be negative, and both cos and sine are negative. And then in quadrant 4, Now your x-coordinate is positive, and your y-coordinate is negative. So one of the things I was saying was when you have to memorize the whole thing, it's not so bad because if you know what's happening in the first quadrant, everything in the family is related. The only thing that's different are positives and negatives. They follow the cast rule. They also follow natural rules of coordinates. Every coordinate in quadrant 2 is going to have a negative x-coordinate and a positive y-coordinate. And so that also helps explain why your cast rule works. And finally, for tan of pi over 4, well, you could look at your special triangle. Tan of 45 degrees is 1. You could also do sine divided by cos, and root 2 over 2 divided by root 2 over 2 is going to be 1. In quadrant 2, well, from your cast rule, it's negative. From your coordinates, dividing sine divided by cos, 1 is positive, 1 is negative. Tan is going to be negative in quadrant 2. In quadrant 3, tan is positive. And in quadrant 4, tan is negative again. So now we can do some mental math. This is the fun part. You can now say, well, what is sine of 135 degrees? Root 2 over 2. Okay, Peter, pick someone for cos of 7 pi over 4.
Cos. Sorry, what was the question?
The question was, what is cos of 7 pi over 4?
I'm going to have to go with root 2 over 2.
Root 2 over 2. Good. What is sine of 225 degrees? Cam, pick someone.
I'm going to have to go with Devin.
Sine of 225 degrees. So think back to our legend. Our coordinates on our unit circle can be written as cos comma sine, so our y-coordinate is always sine. So if we look at 225 degrees right here, and we look at our coordinates, sine of 225 degrees will be the y-coordinate, and so it'll be negative root 2 over 2. So if you remember which coordinate is which, now these ones, you've basically got the same number each time, so it's even easier. You can just say root 2 over 2 and kind of say it's either positive or negative. So I'll say root 2 over 2. Strategy would be this, right? Say root 2 over 2 and then pause. See if the teacher says right, and if they don't say right away, then just say negative, because then chances are you'll get it. That could happen in this one. But we can now do all of this mental math without our calculator. And I know we have calculators now, but 100 years ago, 50 years ago, calculators weren't as prevalent. They were non-existent 200 years ago. And so mathematicians were looking for how many of these angles can we figure out? How many things can we do without our calculator? Because we need them for calculations. And if we can do them without our calculator or without tables,
How many were they able to figure out?
well, they figured them all out. But our next one is the 30-degree family. And what we're going to do in this space right here, we're going to make a special triangle. And our special triangle for 30 degrees, or pi over 6, is the same as the special triangle for 60 degrees, which is pi over 3. And the reason for that is if I draw a right angle triangle and I label one angle as 30 degrees, what does the other angle have to be? 60 degrees. So the special triangle for 30 and 60 is the same because it happens to be the same triangle, has a 30, has a 60, if the other one is a 90 degree. Now, Last time we had an isosceles triangle because two sides were the same. Do you know the special name for this triangle? Scalene. And actually, scalene is the special name for a triangle that's not special. It has all sides different, it has all angles different. It really doesn't have any great properties. I think it felt bad, and they felt bad for the scalene triangle because there was like equilateral triangles. Ooh, all my sides are the same. And isosceles with two angles and two sides the same. That these scalene triangles probably felt really bad because they weren't special. So then they gave them the name scalene just to say, this is the name we're going to give to all the non-special. It's kind of a, yeah, the rejects. And it's kind of scaly. It's not a really nice name. I don't know. So this is a non-special triangle. And this triangle here, it was feeling bad because it wasn't special. And I mean, it was a right triangle, so it felt a little bit like it had something going for it, but everything else, not special. And it ran into a friend that was exactly the same, also not special. But they got together, and together they made something special. So if I take this same triangle and I redraw it, and I redraw it on this side here, exactly 90 degrees there, another 60 degrees, these two triangles are identical. When they get together, how are they special? The whole thing makes an equilateral triangle. And so once again, sine, cosine, tan, it doesn't matter how big or how small these triangles are, but now we can choose any number for one of the sides. The easiest number to choose is 2. So if this is 2, that makes this 2 over here. And the reason I choose 2, because on the bottom, the whole length is 2, but if it's separated into two parts, those would both be 1. And now you have two sides of that black triangle. You can do a squared plus b squared equals c squared. And we get square root of 3 as the other side. We now have everything labeled in this triangle. We can do sine, cos, and tan of 30 degrees. So sine, opposite over hypotenuse, 1 over 2. Cos, adjacent over hypotenuse, root 3 over 2. Tan, opposite over adjacent, and again I'm going to rationalize. That'll give us root 3 over 3. Similarly, we can do sine, cos, and tan of 60 degrees. So sine of 60 degrees, well, now it'll be root 3 over 2. Cos of 60 degrees, that will be 1 over 2. And tan of 60 degrees will be root 3 over 1, which is just root 3. So this will help us label our next two families, the 30-degree family and the 60-degree family. So if we scroll up and think about our pi over 6 family, that includes this point, this point, this point, and this point. If we start with our degrees, and I will give you 15-second head start to label the other three. Did you beat me?
Yes.
And check to see if you got the right angles. I will also give you a 15-second head start. With radians. How did he do? 5 pi over 6, 7 pi over 6, and 11 pi over 6. And finally, with the coordinates, so if we look at our special triangle and we say the x-coordinate is cos, cos of 30 degrees was the square root of 3 over 2. So your x-coordinate will be the square root of 3 over 2. Your y-coordinate, sine of 30 degrees, is 1/2. And I'll race you on the coordinates as well. So just like last time, the values in the coordinates in the same family all stay the same. Just the positives and negatives change according to the cast rule or according to where x values are negatives and y values are negatives. And finally, tan. Guess if I don't give you a head start, it's not really that fair. And so all of your pi over 6 family for tan is root 3 over 3. Some of them are positive, quadrant 1 and quadrant 3, and some are negative, 2 and 4. Mental math. Devin, pick someone for tan of 7 pi over 6. Jake. Square root 3 over 3. Pick someone for cos of 5 pi over 6. Negative square root 3 over 2. Perfect. Pick someone for sine of 330 degrees. Sine of 330 degrees. Negative a half. Do you guys want your brains to hurt just a little bit more?
Yes.
Yes? Okay. I will throw in some negative angles. So, pick someone for sine of negative 150 degrees. Negative 1/2. Can you see that negative 150 would be coterminal with 210? And so then you still just need to look at your y-coordinate for 210. What about cos of negative 7 pi over 6? Cos of negative 7 pi over 6. You get to choose. Yow. Cos of a negative 7 pi over 6. So negative 7 pi over 6 is going to go in this direction. And one of the ways that I think of it is I first think positive. I think if I'm going 7 pi over 6, you can see that that's in quadrant 3. So if I go negative 7 pi over 6, I think about going 3 quadrants the negative direction, which actually ends here in quadrant 2. So negative 7 pi over 6 is coterminal with 5 pi over 6. And cos of negative 7 pi over 6 will then be the x-coordinate, negative root 3 over 2. Awesome. Okay, let's do our last family. Those are the points on our pi over 3 family or 60-degree family we'll start with our degrees. Well, I will put degrees and radians on there. So this is 60 degrees. Pi over 3 radians. Again, I'll give you 30-second head start for both of them. Soon. Yeah. How did you do? And then looking at your special triangle, we can label our points. Cos of 60 degrees is 1/2. Sine of 60 degrees, root 3 over 2. And we can label the other values as well. And finally, looking at our special triangles, we can do tan of pi over 3 and get root 3. You could also get that root 3 by dividing the sine divided by the cos, but then you'd have to remember, how do you divide a fraction by a fraction? You multiply by the reciprocals, and it will simplify to be root 3. So what you need to be able to do is know all of these values. And we're going to have a quiz on Friday where you have to have all of them combined onto one piece of paper. It's the only quiz of the year that I give you before the quiz. I give you the exact quiz today. And you have until Friday to get it.